Hi, welcome everyone to session 7. So in this session, we will discuss about multiple linear regression. In the last session, session 6, we started with an overview of machine learning, what is machine learning, and then we built a simple linear regression model. We took the example of predicting the resale price of an used car, and we predicted the price with respect to just one variable, what is the age of the car. But in this session we will actually explore further. We'll take more variables and predict the resale price of the car. So before we start, um, if you have not watched the previous session video, please watch that, because this is a continuation from the previous session, and we will use the same notebook that we have used in the last session and continue and complete that notebook in this particular session. And for that, of course, I have also created a new folder in the GitHub directory, session 7, and I have uh, retained the worksheet that we have used in the previous session, and of course, a new worksheet, which of course we'll be using in the current session as well. So let's go back and begin, and click on the regression used car price worksheet V1, and you can execute until the step of building a model with more variables, the section 3. You can click here and say cell run all above. So you will come to the state which you had completed in the previous session. But of course, I'm going to give a quick 1 or 2 minute overview of what I have done so far. So we've taken this data set of final cars Maruti.csv, which was an output of our EDA process, where we have collected, processed, and cleaned the data to obtain this few variables and their impact on the resale price of the car. And then in this case, we are actually trying to understand the relationship between just age and price. And we see the negative correlation as the number of years that you drive the car reduces the resale price of the car as well. And we have built a simple linear regression model which looks like y equal to beta 0 plus beta 1 x, and beta 0 and beta 1 are your intercept and coefficients, as you've already understood, and the optimal value for these two are obtained through minimizing an error. It's called MSE, the mean squared error, which is the difference between the actual and predicted value and square, and taking an average of it. And again, from the last session, we have discussed that two different methods are there. One is called OLS, or ordinary least square method, and the second one is a gradient descent. We will discuss gradient descent in detail little later, but let's look at the building the model first. And we set the variable x to age and y as the price. We split the data into train and test, the ratio of 80 to 20%, and we built a model by fitting the train data, which gave us a model of the intercept and coefficients, which looks like the price of the car is 7.62 minus 0.495 multiplied by age. And this is the regression line, which of course we can visualize, because just using one variable we will not be able to visualize moment to start more variables. Then we predicted on the test data to evaluate how good or bad the model estimates are by predicting on the test set, and then we looked at the actual y value and the predicted value of y and the residual, which is EI, which is the difference between the yi minus the yi hat, right? This is the actual and this is the predicted value. And when you calculate the RMSE, the RMSE comes out to be 1.62. Okay, so that's in terms of lakhs. So at an average, you're making an error of 1.62 lakh rupees, which is a quite high, and it's understood because it's just taken one single variable, one information called age to predict. So that is supposed to give a quite high error. The moment we use more variable, more information about the car, the accuracy for the prediction would be much better. And we also calculate the R square value, which gives an absolute value of accuracy between a 0 and 1. And the closer to 1, it is better model, which is explained variant. So y equal to beta 0 plus beta 1 x plus error. So what's a total variance, or you can think like information in the y that can be explained through the model and which cannot be explained. So this is unexplained variance, and this is explained by the model, and this is of course a total. So what is the proportionate of this with respect to total? So higher the unexplained, the lower will be explained. And the lower the unexplained, the higher will be explained. So in this case, it comes out to be 47. So this is 0.47. So you can say this is 0.53. So we're halfway the mark with just one variable called age, which is of course a significant variable when we actually think about the resale price of a car. But that's not sufficient. We have to add more variables to build the model. So what we'll do is we will, of course, I have also given an exercise to add one more information called kilometer driven, and I assume that you would have done this exercise. So just with age and kilometer driven, what's our RMS and R square. But beyond that, let's build a model with more variables. The reason here I'm taking only 3 variables is when you build a model, you may not have enough information collected. Of course, in this case, we are already given with the CSV file. In the real world, you may not have it. You have to go and collect it. So you will start with saying that, okay, what is the most important information to predict the value of y? So in this case, you can think like, what are the most important questions the customers ask when they plan to buy a car, an used car, right? So typically the 3 most important questions customers ask. Of course, it could be more, but let's take an assumption, and we'll probably agree that these are the 3 most important questions people ask: what model it is, what car model it is, right? And what is how old the car is. So for how many years the car has been driven, and how many kilometers driven, right? 3 most important questions, 1, 2, and 3. Let's say with these 3 important questions, how much we can predict. So we'll go and collect only 3 variables and predict. In this case, of course, we have the data. We'll just select those 3 variables and build the model. So this is called multiple linear regression. The simple linear regression is when you build a model with just one variable, beta 0 plus beta 1 x. So this is basically called your simple linear regression. But when you build a model with multiple variables, so you will have beta 1 x1, beta 2 x2 plus beta 3 x3, and so on and so forth. In this case, 3 variables, let's say. So this is called MLR, or multiple linear regression. So we will actually estimate the value of y with respect, by taking the information from 3 variables. So we will know each variable has what kind of influence on the outcome, right? So beta 1, beta 2, beta 3 will be with respect to each of the variables. And but before we build a model, if you look at the variable types of the factors that we are considering here to build a model, of course, how old the vehicle is given by age, which is numerical in nature, and how many kilometers driven is also numerical in nature. But what a model it is, whether it is a Swift model or it's an Alto model right? Or it's a Baleno model. These are of course the different models, different possible values for this particular variable, but this is a categorical feature. But how do we incorporate this into a categorical feature, into the model? So you cannot build a model saying y equal to beta 0 plus beta 1 age, right? Plus beta 2 model directly, right? Because this value will be multiplied by the coefficients. But this value is a string value. It's a Swift, Alto, or Baleno, or Sia, whatever it is, right? So we have to convert this variable into certain numbers. So in this case, let's say we call it numericalize it. When you convert something, you call numericalize it. So what are different possible options we have to convert this model information into numbers? So let's look at what are the possible values. If you go back and scroll up and look at it, the possible values are this. Let's say from these 5 samples, Attica is one possible value, Swift, Alto, and Wagon. Now, one way is to kind of enumerate them. We can say, okay, let's assign a value to 1 to Attica, 2 to Swift, 3 to Alto, and 4 to Wagon, and so on and so forth. So what I can do is, we can look at a categorical feature and find out what are the unique values, right, in that particular variable, and each unique value is given a number. Okay, you can just level them, enumerate them. This is also possible, but typically it's not used as the right approach because this quantity information is actually wrong information. Just for the example, what the model will think that Wagon is basically 4 times more important than Attica, 4 times more influence, right? So whatever the value is estimated on the price, which is not a correct information to be encoded because they are all independent and will have a different influence in the model outcome or the price. So the alternative approach, of course, there are many approaches are there. We might discuss some of the advanced approaches in a future session, but what we will discuss in this session is the most widely used approach people take to encode the categorical feature. And this is called OHE, or it stands for one hot encoding. This is also called dummy variable creation, right? Why it's called dummy variable creation? So in this approach, what we do is we first find out what are the unique values, right? And for each unique value is converted into a variable by itself. So the model as a variable will not be leveraged here. Instead, we will create a variable called Attica, right? Will create called Swift. We'll create a variable called Alto. We'll create a variable called Wagon. So these are not actual variables. They are unique values from the categorical variable, but we are going to create a variable by that unique value. And these variables are actually called dummy variables. They are not actual variables. They are only created from the perspective for the model building. And then let's look at a car, this particular car, because it's Attica car, we'll set it to 1. Attica is set to 1, and Swift is 0, Alto is 0, Wagon is 0. So in a way, we are saying that this is a Attica car, not a Swift car, not a Alto car, not a Wagon car. Let's say people typically pay a little higher price for Attica compared to Swift, Alto, and Wagon. Let's make that assumption. Then when we build a model, what happens is we build a model saying that y equal to beta 0 plus beta 1 Attica beta to Swift, and so on and so forth, right? And when it's set to 1, what are the price people additional price they want to pay for Artiga, that gets added to the Y value, whereas all the values remains 0. And if it's a Swift car, then this becomes 0, and whatever the premium people want to pay for the Swift car, so that can be added to the model, so on and so forth. Okay. Now, how to do that? So let's go back and do this part of building multiple regression. The first step is feature set selection. So in this case, what we do is we first identify what all features we're going to use here. So of course, model is one feature, age is second feature, and KM driven. So 3 features: model, age, and kilometer driven, with the based on the question that you are asking. And then because one of them is a categorical feature, we are going to create a dummy variables for that. So what I can do is we can use pd.getDummies. So pandas has a method called getDummies, which takes the data frame. So in this case, we will take all the 3 variables: model, age, and kilometer driven, and then it takes a parameter called columns, which is now in this case model. So the column which would be converted into dummy variables is given here, either one, or you can also give a list of columns, and the remaining columns which is not specified here is automatically assumed to be numerical feature, and they are returned as it is, and this particular column would be encoded into dummy variables. Let's capture all this information into a new data frame called encoded cars df, which contains all the new information. This has to be given as a list model. And then encoded cars df, if you look at the first few records, now you can see age and kilometer driven has been retained as it is, but the model variable, which is converted into dummy variables. So there is a variable called A star, car, Alto, Baleno, Celerio, Ciaz, and so on and so forth. Right? And how many total variables have been created? So encoded cars df.info, or you can just look at the shape. So 16 variables now. So 2 of them are numerical, and the remaining 14 new dummy variables have been created from the model, because there are 14 unique values in the model, which you can also again check from cars df dot model dot unique. So these are the unique values, and if you look at the length of that, right, there are 14 unique values. So for each one, it has been created one variable. And now what we'll do is we will take this as my x features. So this will be my now x1, this will be x2, this will be x3, this will be x4, and so on and so forth. And let's set our x and y variable now. So x would be what now? The encoded cost here, and y will be the cost df dot price. And let's split the data first into train and test before building the model. So we have already imported train test split in the simple linear regression model building. We have done here train test split. We are just going to do the same thing here now and split the data. So you can say x train, either you can copy paste and write it y train y test equal to train test split x comma y x comma y, and then you can say train size, which is 0.8, and let's say random state, right, equal to, let's say 40. So as long as we keep this number same, we should have gotten the same split in train and test. Now if we look at extreme, there are 807 rows now, and X test, if you look at there are 202, and if you look at the complete X, the 1009 total samples are there. Out of that, 807 has gone to train, and the 202 has gone to test, and then in the complete random fashion. You can look at that as well if you want. So extreme, let's look at the first 10 records, and you can see this is the index, and you can see these indexes are completely random. So they have been taken completely random from the initial subset. So they are not taken in any particular sequential order. And because we have used random state 40, if you also use 40, you would exactly see the same indexes here as well, because that's a seed value. Now let's go and build a regression model. So now the model look like beta 0 plus beta 1 x1, beta 2 x2, and beta n xn, in this case 16, because we have 16 variables. And let's call it v2, the regression model v2. So linear regression lreg v2 dot fit, and we'll supply the x train and y train values. And the model is built now. That means it would have found the optimal values for beta 0, beta 1, beta 2, beta 3, and so on and so forth, for which the MSE is minimum. The mean squared error is minimum. Of course, it uses ordinary least square method. And let's look at those estimated parameters, beta 0, beta 1. So lreg v2 dot intercept comes out to be 6.79, and the coefficients comes out to be, there are many because we have 16 variables now. So intercept is 6.79, and the coefficient is about 16 of them, and those coefficients in the same order as the columns in the extreme, right? So what you can do is you can map them into a dictionary and visualize them. So there is a nice function called zip in Python, which we have discussed in the Python primer session, the first session. So what you can do is you can say extreme dot columns and lreg v2 dot coefficients. So it maps what is the coefficient for age, what's the coefficient for kilometer driven, what's the coefficient model A star, and so on and so forth, isn't it? These values have the precision decimal values many places, so you can round it off by saying np dot round, and let's say 3 decimal places, and you can see now. And this looks like the model is the price of the car is 6.79 lakhs and minus 0.325 multiplied by age minus of 0.005 multiplied by kilometer driven. Remember, this is 1000 kilometer driven, minus 1.861 for Alto, right? Plus, let's take CRs here, 2.177 CRs, and so on and so forth, all the 16 values. Now, when you know the car, let's say the car is CRs model, and it has driven for 5-year-old, and driven for, let's say, 20,000 kilometers, right? So this should be as simple as for a CS car, it will be 6.79 minus, because it's a, let's say it's a 5-year-old car, age is 5, kilometer driven is 20,000 kilometer driven, and CS car, right? Then minus 3.25 multiplied by 5 minus 0.0505 multiplied by 20 plus 2.177. Okay, so that would be the estimated value of the car, right? So the plus means the, the think like the premium that people want to pay for that particular model, and negative means the lesser price people are ready to pay. The price gets reduced by that much. Okay, so that's how the model parameters has to be interpreted. So this looks good, but we still don't know what is the accuracy of the model, whether the model is good or bad, and which of course we can understand by predicting on the test data. The only way to evaluate the model is, of course, by applying the model to the unseen data, in this case we have taken out a test data which contains 207 samples, and we're going to predict on that. So let's call it ypred2 and lreg v2, that's a model, and there's a function called predict which takes your test data and makes a prediction. Now how these predictions look with respect to the actual values, we can compare it, but let's capture that into a data frame first, which is a wonderful way to kind of compare and see it. So I'll create a data frame in which we can create a column called actual and store the value of the test data, and we can create a value called predicted and store the value of the predicted values, and then the errors, which is, let's call it a residual. So y test minus y pred 2, right? And let's build this particular data frame. And now if you look at ydf2 dot info, we have 3 columns now: actual, predicted, residual. And let's look at some test data randomly. We'll sample from df2, let's say sample 10 randomly, and here it is. This is the test data which is randomly taken, and which is of course not part of the train data, it's part of the test data. And this car was actually sold at 7.4 lakhs, but predicted as will be sold at 7.13, pretty close to the actual value, an error of 0.26. Okay, so this is actually underestimation. So in this case, positive means underestimation and negative means overestimation. So you can see 26,000 rupees, 11,000 rupees less, 95. This is a little higher error, this is higher, but this is lower. So you can see there are some quite low and little bit higher, which if you compare with respect to the previous model where we have seen higher errors. Now if you see here, the previous one we have seen error like 3.3 lakhs, 2.1 lakhs, 2.9 lakhs, 3. You can see higher errors are there, right? And that seems to have come down now with respect to by using 3 variables now, and looks like this is a better model, right? But we can actually measure the actual accuracy or error of the model by looking at the specific metrics. So let's do that now, measuring accuracy. We can calculate R square, and which takes again the actual value and the predicted value. So all the metrics will take the actual and predicted value and calculate the metrics, and which gives us some indication of how good or the bad model is. So in this case, it says is about 0.85. Okay. So this is pretty close to 1, and seems to be a very good model. In fact, as a thumb rule, any model which is more than 0.8 is typically called a good model. So more than 0.9 or close to 0.9 is typically called an excellent model. But as we discussed in the last session, this has to be understood from the context of the domain, because the good and bad model judgment could differ based on the domain itself. In certain domains, because of the high uncertainties, even 0.5 and 0.6 itself, it's called a good model. But in this case, we can still see, 0.85 is typically a pretty good model. And how much error you are actually making in this case, let's calculate the MSE V2, MSE2, and we know there's a function called mean squared error, which again takes the actual value and the predicted values. So MSE2 and MSE2, we can take a square root of it because this is square term, and we can still take a squared value of it, RMSE underscore 2, and which comes out to 0.881. So this is of course in the unit of y, that's about 81,000 rupees. So we are making an average error of about 81,000 rupees for the predicted value. So if you say the car will be sold at 5 lakh rupees, right? So plus or minus of 0.81 at an average, of course. Okay, we look at the interval of it little later when we do error analysis, but this is how much the error we are making here. This is definitely better, much better model compared to just using one variable, and we have used the most important three variables: the model, kilometer driven, and the age. Of course, if you add some more variables, then for example, I've given the participant exercise 2 here, you should attempt it. So beyond these three variables information, people also ask two important questions, like what transmission type, it's an automatic car or a manual car, or they're also asking questions whether it's a petrol or diesel car. So these are the 5 most important questions people ask, besides of course is a first owner or second owner, but these are the 5 most important information that can be leveraged to estimate the price of the car, which will take you to almost probably 90%. And then of course any more information will typically push the model's performance beyond that. So what we'll do now is we'll go ahead and build the full model. We'll build the model with all the variables that we have, because we have total how many? So we have a location, fuel, so these are categorical features: C1, C2, C3, C4, and model C5. So 5 categorical features, and numerical feature N1, N2, N3, N4, N5. So there are 5 numerical and 5 categorical. So 10 variables are there, and price is of course your Y variable. So what we'll do is we'll go and build a model with all the variables, and in this case of course we have to encode all the categorical features before we can use that in building the model. So let's do that. So let's go to the step 4 and build a multiple linear regression model with we'll go into step 4 here, building a model with all the variables. So in this case, we'll do a feature set selection first, like we in the previous one we used model, age, and kilometer driven. So here X features would be all the columns. So when you all the columns, either you can explicitly specify, or what you can do is you can say cast df dot columns. So you can use this variable to populate this X features. Now if you look at X features, it contains all the variables, but one of the variables is called price, which is our outcome or target variable, which has to be removed from the X features. So in the list, Python list, there is a function called remove, which removes the value from the list. And now if you look at X features, now it contains the actual features names, the column names, which should be considered as a features. And the price is removed, which will be of course the Y value now. So what we'll do now is we will encode the categorical variables out of this X features. So let's create a variable called cat vars or cat features some name and specify the categorical features here. So these are the four variables. Location, we have a location, fuel type, transmission type, and owner type. Of course, there is one more there, model. So these are the five cat features, right? So the num features would be, typically when you build a model, you make a list of all the features and then you also categorize them into categorical and numerical features, right? So numerical features will be remaining the five ones. So either you can explicitly specify or you can subtract this list from this total list. We can do that. So we can just set, because we can do a set operation cat features. So this will take the difference and will convert them into list because we need to store them as a list. And if you look at num features, now power, age, kilometer driven, mileage, and seats, these are my numerical features. So now let's encode the categorical features first. So encoded cars df will be cars df. Sorry, we'll use pd dot get dummies. So I'll supply the complete data frame with all the features, and then in the columns parameter we will specify out of those X features which are going to be or which are to be considered as categorical features. So we have a list called cat features. So out of n X features, these features would be encoded as dummy variables and remaining ones would be returned as it is into the encoded features. If you look at now, let's look at only a few records. Let's say 5 records. So seats, age, mileage, power, and kilometer driven. So these are the 5 numerical features which are retained as it is. But if you look at the other ones like location, right, and model, remaining all has been converted into 0, 1 values. So total how many variables have been created? About 37. You can also look at that. We encoded in columns. So these are the numerical features. For location, it is created. For fuel type, petrol, diesel, transmission, automatic, manual, owner type, model, and all the dummy variables have been created. We can also use, for example, here fuel type petrol and diesel, right? So when diesel is 1, petrol will be 0. When diesel is 0, petrol will be 1. So rather than using two variables, we can just use one variable and remove the other redundant variable. Um, we can pass a parameter called drop first true, which would actually do that. So if I just say drop first equal to true and re-execute this, and if you see this here, the fuel type is petrol. There's no diesel created because now that's redundant. Transmission is only manual, and so on. So for all the categorical features, if there are n categories are there, if there are n categories are there, so n minus 1 variables would be created. So this reduces the dimension of the data set now. So now it's become 32 columns because there are 5 categorical features and the base uh, value of the category has been removed. This also reduces multicollinearity from the model, which we have not discussed, probably discuss in future. Now let's set the x and y variable for model building. So x equal to, now you can say, encoded data frame, and y will be my cars df dot price. And let's do a data splitting. X train, X test, Y train, Y test, the train and test split, X comma Y, and train size. You can also specify, by the way, test size. So not only train size, you can specify test size. Let's say 20% is my test set. So automatically the other one would be calculated. So in this case, the remaining 80% would be train data. And we can specify the random state. So let's take 40 here. And let's look at the shape of train. Same, we have 807 samples, but 32 columns now because we have more dummy variables. And for test data as well, we have 202 samples but 32 columns. And together, of course, 1009 samples or records are there. So here we have taken quickly all the features. Of course, we removed price because that's a y value, the outcome value. And then we have specified out of all the features which are categorical features and which are numerical features. And we have encoded the categorical features and set an x and y value and split the data. Now we can go and build the full model with all the variables in the training set. So let's build a model. Let's call it LREG V3 linear regression, and LREG V3 dot fit. It's as simple as this. And it has a built-in model now. That means it would have found the intercept and coefficient for all the 32 variables, which minimizes the mean squared error. The most optimal best fit line by minimizing the error of the model, which is mean squared error. Again, how the model parameters look like, we can look at that. So LREG V3 dot intercept, which now comes out to be 5.03, and LREG v3 dot coefficients. You can see there are so many values are there now, right? So there are 1 2 3 4 and 8 32 values are there. But again we can use the zip function to assign or create a dictionary which shows which coefficient belongs to who, so that you can understand that. So for that again we can take the column names basically as the dictionary's key value and the coefficients to be the values of that. And we can do a rounding of this lreg v3 dot coefficients. Yeah. So what I've done is we have zipped the column names with the coefficients. And of course we added one more functionality here to round up the numbers because the values have large number of decimal places. And if we execute this one, and you can see the coefficients for all the values here, columns here. So here again, you can say the price of the car would be, our coefficient is how much? So intercept is 5.03. So 5.03, that's intercept, plus 0.054 seats, minus 0.25 age, right? Plus 0.036 mileage, and so on and so forth. The 32 different coefficients are. So plus means the additional premium for that particular feature, or the value of the y increases with that, right? So every seat you added, the value increases by 5,000 rupees. Every 1 year you additionally drive the car, the seller, the buyer is paying 25,000 rupees lesser, so and so. So you can actually see the positive means kind of premium that it gets added, right? So Bangalore people are typically ready to pay additional 70,000 rupees, but whereas Delhi, there's a negative price. Petrol, you can just say less price compared to diesel. Manual, again less price compared to automatic, which makes sense intuitively, right? People pay 50,000 rupees less to the manual cars. So this is how the model has to be interpreted, right? And then based on that, we can make a prediction. Now we can take this model, and we know that this model would have definitely better accuracy from the previous model, which gave us an accuracy of about 0.85. But how much accuracy we have improved, we want to measure that, then we will go ahead and predict on the test set now. So let's again create ypred 3 equal to lreg v3 dot predict, and we will supply the test data which gives us the prediction values. Again, to compare, just look at, we can again create a data frame. So PD data frame actual y test and predicted value will be y pred 3 here, because that's the lreg v3, and residual would be the difference between y test minus y pred. And if we randomly look at some of the samples now, let's say look at 10 samples. You can see the values, the errors have further reduced now. So this car, which is actually sold at 3.15, the predicted resale value is 3.31. It's an overestimation of 16,000. So you can see the error of 16,000, 18,000, 18,000, 30,000, 7,000, 1,000. Right? The values have reduced. Of course, there are still some large errors are there. We'll go and check which are the large errors. But seems to have the residuals have errors have reduced even further in comparison to the previous model where we have used only 3 variables. Now we are using all the 10 variables. Of course, the more and more variables that we add, the marginal increment and the accuracy would start diminishing. So the the increase in the accuracy will flatten out. But how much this particular model is making in terms of accuracy and error, we can compare that again by looking at the actual and predicted values and the R square metrics. Yes. Now the accuracy has gone up to 0.91, 91%, which is quite high. On the relative term, the thumb rule is quite a good model. And what's an average error that we make when we make a prediction? Again, MSC 3, you can say mean squared error, and we can copy paste this one. And RMSC 3 would be NP square root of MSC. Okay. And let's print the value of RMSC now. So about 60,000. So the first model gave about 1.6 lakhs, then it came down to 85,000, now it's come to 61,000. So when you, at an average, you're making an error of, let's say the actual value is 5.5 lakhs, an average of 0.60 is what we're making an error. We'll also look at the interval when you do the deep error analysis. So this is a good model, very good model, excellent model in fact, anything more than 0.9. So that means if you look at my explained variance, so y equal to the model beta 0 plus beta 1 x1 and so on and so forth plus error. So the total variance is 100. The explained variance is about 0.91 and only 0.09 is not able to explain by the model. And this 0.09 could be random error, noise, or could be not explained through whatever factors that we have. So if you look at what are the reasons for the remaining error, if you want to understand that, there could be several factors, right? One could be more features and factors. For example, we know that in this particular data set, there are some important information which are missing. One could be the insurance claims history. Insurance claims history, which is not available. And people typically ask this kind of information to estimate to the resale value of the car. So this is, of course, a very important information. And if you add that, definitely the accuracy of the model will typically go higher. Or maybe the condition of the car, which is again very difficult to collect reliably, because if you ask the user might basically say it's good condition, but you should find a reliable way if at all you are capturing that information. But it's very difficult. Sometimes it would need additional cost and effort to collect this information, which can definitely enhance the accuracy of the model. Sometimes you have to also think about the reliability, right, in capturing this information. But of course, when you add this will increase the accuracy, and which is a necessary step, especially if that model is not giving a good accuracy. So in our case, it's still giving good accuracy, And if you still want to improve, you still may have to collect more data. You can also collect more samples, that number of records, but you cannot just go and quickly randomly collect some samples. We have to do some error analysis to understand what kind of samples might help. I'm just giving an example. Let's say when you do a deep error analysis and you find that um, maybe the Swift cars, right, typically has a higher uh, error compared to other models, then you probably will go and collect more data about the Swift car. Let's say this is underrepresented in the sample set. This could be model, this could be also a location. Let's say for a particular location you don't have enough samples, and that location typically has higher error compared to other locations. So you'll go and collect more data about that location. So you cannot go and just randomly collect samples. You have to go and do little bit of deep dive into error, which of course we'll do as a step, the next step, and look at that. You can also build complex model, which is of course immediately you can do, because here we are only building a linear regression, right? A linear model, which of course has an assumption that your variable, your factors linearly influence the y value. So when the x value increases, it linearly, the y value increases linearly with it, with the beta coefficient. But what happens if the x has a non-linear relationship, like a quadratic or polynomial, right? So some of the models like decision tree or polynomial regression, right? Other models can capture those relationships, and which can increase the accuracy if such relationship exists in the data. So, and this can be done immediately because we have the data. We can just go and build different models, let's say decision tree model or KNN model or a random forest model, and check the accuracy, which of course we'll explore in the future sessions. And these are called model experiments. You're experimenting with different models, right? And this is of course a step, because we are achieving simplicity. This leads to higher error. We can actually try. So any of the things might work. In what sequence, when to apply and all that, little more deep dive we will do in the future session. But as of now, let's just understand at a high level what could be the reasons for the remaining error. And then of course noise and randomness. That means certain information cannot be captured, and of course if you, even after providing the exact information to different buyers, two buyers will definitely not quote the same price. There will be some noise will be there, right? And some information cannot be captured. Like one of the most important information in this perspective is called urgency. How, let's say the seller wants to urgently sell the car because he or she is moving out of a particular location, or he or she wants to buy a new car, or similarly the buyer also wants to buy a car urgently, so they are ready to pay a little higher premium, but they may not specify that there is an urgency, right, when they're actually purchasing the car. But that information is not captured, but definitely that variable or factor influences the resale price of the car. So that can never be captured and will always lead to noise, right? So these are some of the reasons that could actually could be the factors for the remaining error, and you can take certain steps to reduce the error or improve the accuracy of the model. Okay. So now what we'll do is we'll go and look at the error analysis.